Hello everyone, welcome back to Spectrum classes. In this video, I am going to discuss about the Born-Oppenheimer approximation. And this is the most fundamental approximation in chemistry, and this tells us about the emission and absorption spectra observed in the molecules and how these transitions occur in the allowed energy states, that is ground and excited energy states. So I am just going to tell you the Born approximation and the derivation of this approximation because this is asked in many of the exams. So these are the electronic energy levels and these are the vibrational energy levels, and among these vibrational energy levels we are having rotational energy levels. So here let's start with the Born-Oppenheimer approximation. This is the most fundamental approximation in chemistry since energy level scheme in molecules is different from that of the atoms and is relatively complicated, as I am going to show you here. So this is complicated, as you can see many number of energy levels in between the two electronic energy levels, which is not the case in case of atoms, right? So this type of energy schemes we have already discussed in the atomic term symbols. So the main reasons for this type of complicated energy level scheme in the molecules is that we cannot classify molecular energy states according to the electronic angular momentum L, as we did in case of atoms. This angular momentum in case of molecule is not conserved actually. Here I am going to show you one example. This example I have already discussed in my molecular term symbol video. So I will give the link of this video in the description box. So for diatomic molecules, the total charge distribution is symmetrical about the internuclear axis. Here you can see. And so that the concept of angular momentum about the axis is conserved. So here this you can see, this is the conserved angular momentum in case of molecules, and it is used to classify molecular energy states. Now the second point is the internuclear motion in molecules cannot be ignored, as we can do in case of atoms, because nuclei vibrates along the internuclear axis, and in addition the whole system rotates about its center of mass. Here I am going to show you this. Fine, so this is rotating about its center of mass. This point we are going to discuss in case of rotational spectroscopy. This we are going to discuss in detail in case of vibrational spectroscopy. So the energy of each rotational and vibrational levels are quantized, and as a result there are many more energy levels in molecule than in atoms. So that is why this understanding of this Born-Oppenheimer approximation is very important, because how it is generated, so that depends on the nuclear and electronic motion of the molecule. So as a whole we have to derive the Schrodinger wave equation for this type of systems, right? Now how we are going to derive the Schrodinger wave equation for a given molecule? So to study the molecular system quantum mechanically using the Schrodinger time independent equation, writing the Schrodinger equation for the system is the first part. So for this type of system, how we are going to write the Schrodinger wave equation? So we are following this formula to write the Schrodinger wave equation. So for a given chemical system which is having n nuclei and e electrons, the total number of terms, that is kinetic and potential energy terms in Hamiltonian, can be calculated by using the given formula. So here is the formula to count the number of terms in the Hamiltonian, which is equal to n plus e into n plus e plus 1 divided by 2. So here n stands for number of nuclei and e stands for number of electrons. So this many terms will be incorporated in the Hamiltonian, right? So it is further divided into two parts. One is kinetic energy terms, which is equal to number of nuclei plus number of electrons, and the second is potential energy terms. So the potential energy terms are further categorized as VEN. This subscript represents the electron nuclear attraction, which is equal to N into E terms, right? So here the attraction is given by this. So this electron is attracted by this nuclei, and this electron is attracted by this nuclei, and it itself attracted by the nuclei to which atom it is belonging, right? So this type of interaction is also present. Now coming to the next term, VNN. So here this subscript NN stands for nuclear repulsion, and for this many terms are incorporated. So here you can see this nuclear repulsion term. The next term is electron repulsion term, and this many terms are incorporated corresponding to this type of interaction. So here is the electron repulsion. So I will explain all such terms in the next slide. So here first we are adding all these terms, kinetic terms and potential energy terms. So kinetic terms are represented by the T operator, right? And potential energy terms will be represented by this V operator. And as a whole, the Hamiltonian will be comprises of this many terms, as we discussed in our previous slide. So here what this kinetic energy operator term means. So N stands for nuclei. So if we are having 1, 2, 3 up to alpha nuclei, then this kinetic energy term can be written like this: summation of alpha h square upon 8 pi square m of alpha. This is the mass of the alpha nuclei. And del 2, this is the del operator, right? It has its usual meaning, so I have not written over here. H is the Planck's constant, m is the mass of the alpha nuclei, and on summation of all such terms for the nuclei present in the given molecule. And this is the operator term for kinetic energy operator, right? So this is we have already discussed in the Schrodinger wave equation. Now in some of the texts you are going to see this term in this format, right? So here what happens, here is the H and here is the H cross. So this H cross means H upon 2 pi. So this 4 pi square incorporated into this term. So the leftover term is this much. So in either form it is given in the textbooks, right? And this kinetic energy operator for the electron is again given by this type of representation, and here all the terms have their usual meaning, and here this del I represents the, it is operated on electronic term, and this small m represents the mass of the electron. Similarly, I will also elaborate all the potential energy terms here. So the potential energy term for nuclear repulsion is ZA, ZB, E square upon 4 pi epsilon 0 R, and here I have written this subscript R, since ZA, ZB be the charge on the nuclei, right? Here R is the distance, and this R dependent on the internuclear distance, right? Similarly, for electron nuclear attraction, we are having this term ZA square upon 4 pi epsilon 0 R. R is the distance again, and this distance depends on the nuclear and electronic coordinates, right? The next term is electron repulsion. So here you can see here E square upon 4 pi epsilon R, and this is depends on the internuclear distance, right? So R terms is representing here distance, and this subscript represents on which parameter it is dependent. Fine. These all the terms have their usual meanings. Fine. Now on writing this, all these terms in this Hamiltonian, so the Hamiltonian will be looks like this, right? So this is minus, minus, this is plus, this is minus again, this is plus. Fine. But writing in this manner is very difficult, so we will move with this type of representation for this Hamiltonian. Fine. Now this Schrodinger wave equation for the molecule can be written as, and here E is the total energy of the molecule, psi is the total wave function for the molecule, but the complication is that the proton being about 1840 times heavier than the electron. So the electronic motion is extremely fast compared with the nuclear motion. If it is assumed that the two motions are independent of each other, which is a part of the Born-Oppenheimer approximation, then the total wave function can be written as a product of electronic as well as nuclear wave function, which is represented by psi e and psi n. So here I have just represented by this. In some of the textbooks you will see in this manner. So this is a little earlier to understand these parameters, right? So psi is dependent on R and R. R is the internuclear distance and small r is the electronic distance between the electrons. And this nuclear wave function depends on the internuclear distance. So according to the Born-Oppenheimer approximation, the nuclear kinetic energy is neglected, or the nuclear coordinates are assumed to be fixed while writing the Schrodinger equation for electronic motion. So we are going to understand this part in the next slide. So see, I have mentioned over here that being heavier than the electron, the kinetic energy of the proton is very less. So here I am just going to show you this. This is our total Hamiltonian, and this part being its sluggish motion, it can be eliminated or neglected from the electronic wave function part. But here we are just considering separation of variables. So this is in terms of electronic wave function. So these terms incorporated in the electronic wave function. And here the problem is this part depends on the nuclear wave function, so it restricts us to separate the variables in electronic as well as in nuclear variables, because the dependence of electronic wave function on nuclear coordinates would be parametric. Means if we fix these nuclear coordinates at a certain value, then this will becomes a constant, and if this becomes a constant, we move it to the right hand side. So here what we will get, E minus VNNR. So if this is a constant, so this part will also be a constant, and this will change the eigenvalues of total energy, will give electronic energy value. So in other words, we can say electronic energy value eigenvalues are shifted by a constant value. So this E depends on the nuclear coordinates, as I told you earlier. So here this R becomes just a parameter, and this V and N becomes a constant and shift the eigenvalue by a constant number. So this equation which I have previously written, so this equation can be written as this EE. Getting my point? So E minus VNN can be replaced by this EE. Just this represents the electronic Hamiltonian part, right? Now this HEE again I have written over this. Now coming again to the whole Hamiltonian part of the molecule. So if we are considering our nuclear coordinates, so nuclear coordinates can be written like this. So TNN, this is the kinetic energy of the nuclei, and rest of the terms here I'm just going to put, so this part and this part and this part, these three parts all together will gives us this EE. Now this equation will be converted to this form. So here is the kinetic energy of the nuclei, here is the potential energy of the nuclei, and here is the eigenvalue of the electronic wave function, right? So the nuclear wave function depends on the electronic wave function. I am just going to show you here. So this, now you further understand that the kinetic energy and the potential energy of the nuclei, as we know that Hamiltonian for total energy is equal to this much, right? And it gives the total energy value. So here this and this part will be replaced by the Hamiltonian. Clear? And now this part remains as such. And here is the total energy of the molecule, and psi n is the nuclear wave function here. Fine. So in some of the textbooks it is written like this, that the kinetic energy remains as such, potential energy of the this and these two terms collectively written as potential energy for the nuclear wave function, right? So in either way you can write down, both have same meaning. And further, if you want to replace this as in the form of Schrodinger equation, so this is written as Hn star. Hn star means effective nuclear Hamiltonian. So here effective Hamiltonian, it contains the characteristic eigenvalue of the electronic wave equation as part of the potential energy. So this is having the same meaning for the nuclear motion along with Vnn. Getting my point? So you do not misunderstood all these terms. So if you are writing in this form, so here Hn is written. If you are writing in this form, so here what is written? Tnn. And both gives, this and this gives effective Hamiltonian part. And if we write in this form, this you can write down in this form. Fine. So both have the same meaning. Okay, fine. One point is there to which may bother you. So here psi nn, why we have chosen this psi nn instead of psi? So as I told you earlier, that psi is comprises of psi e and psi n. Fine, we understand. Now the question comes where this psi e goes. So you need not to worry. I will explain it in alternative method of derivation for this Born-Oppenheimer derivation, right? Now we are moving to the conclusion part. So this Born-Oppenheimer approximation enables us to solve the complete molecular wave function in the following way. So here this is in two parts, right? One is the electronic part and the other one is the nuclear part. We are first going to discuss this electronic wave function, right? So this electronic wave function is a function of both nuclear coordinates and electronic coordinates. But in this case, nuclear coordinates were fixed or that are parametric. So parametric means at a time we fix the nuclear coordinates. So this can also be understood. The electronic wave equation for a given electronic state of a molecule is solved for a range of values of nuclear coordinate. Means we are having one part, one value of nuclear coordinate, then this gives one set of psi e and eigenvalue of electronic states, and that will be continuous function for the nuclear coordinates, right? And in this manner we will get the potential energy curve. Here you can see. So here you can further understand the electronic wave function for a given electronic state of the molecule is solved for a range of values of nuclear coordinates. So here is the r is the distance between the nuclei. So if we are just plotting the graph between energy, eigenvalues, energy and distance of nuclear distance, then we will get different values, and here we will have the equilibrium value of Re. This is the distance Re, equilibrium distance for the nuclei. If we are moving this side, means we are decreasing the internuclear distance, then we are having this type of energy curve for this electronic part of Hamilton, for this electronic wave function, right? And this is the continuous function of nuclear coordinates. That is why we are having this type of curve. We get a potential energy curve for a range of R. So here we are changing the R. So this is the main crisp of this part. Now coming to the nuclear part. So by knowing that electronic eigenvalues, we are putting these in the nuclear part and we are getting the expression for psi n and E, right? So here eigenvalues E are the characteristic energies for the whole molecule in the given electronic state. So this statement is important. A set of psi n and E are obtained for each electronic state of the molecule. So if our electronic states are fixed, we will get a set of psi n and energy eigenvalues, right? So it further understand the term psi n is the function of nuclear coordinates and depends upon the vibrational and electronic quantum states. Means it describes the rotational as well as vibrational motion in a potential field supplied by the electron. So what does this mean? Potential field, why we are saying this? So this comes from Vnn plus Ee, right? So potential field, and this gives us potential energy surfaces. And you can understand here we are having the rotational and vibrational energy levels. Though in this part the rotational part is not included, only vibrational part is included. But after putting or multiplying by the rotational part also, and rotational and translational part, we will get the wave function for whole molecule, right? Since E for a molecule is the sum of E translational plus E rotational plus E vibrational plus E electronics. Thank you all. Thanks for watching.